So the aim of the first lab experiment is to implement and explain the uses of a moving average filter, a derivative filter, first order difference, and a derivative filter, 3-point central difference. So what is a moving average filter? A moving average filter is a low pass filter whose response in the time domain can be obtained by taking an average of the signal going backwards in time. Now an L point signal is just taking an average of the L points going backwards in time, the L data points going backwards in time. So in the Z domain, the equation is this and the transfer function is this. Now from this particular expression, you can observe that there should be 8 zeros and 8 poles. However, since one pole and one zero gets cancelled out, there remains 7 pole and 7 zeros. These 7 poles all lie on the 0, whereas the 8 all lie at the 0 point, whereas the 7 zeros lie on a unit circle. The magnitude and phase responses are calculated by substituting z is equal to e power j omega, and after that getting the corresponding real and imaginary parts, then taking the overall magnitude of this particular expression and then getting the phase of this entire particular expression. So for that expression, this is the magnitude response and this is the phase response. Now, why is the moving average filter a low pass filter? Now, the intuition for this can be seen on the time domain itself. So let's assume that we look at something, this particular filter at y is equal to 3, right? And since let's assume that it is an 3-point moving average filter. So if it goes back in time, you take 3 values before it and average them. Three values including that time and one value before that and the second value before the first one. So if you take an average of these 3 values, you get the same signal back, right? It's a single flat line. But if I do the same thing with these 3 values, I get a value that is less than this particular value, right? I get a value that's somewhat here. And if I take these three values, I'll probably get a 0. Now, what is the difference between this signal, and this signal? Well, this signal is 1, which has a frequency of 0. The signal in figure 2 has a frequency higher than that of figure 1, but less than that of figure 3. Whereas from the third experiment that we have seen that the response, the average taken at a particular point, is decreasing as the frequency increases. Hence, it is a low pass filter. And this can be further confirmed by looking at this magnitude response. So the magnitude response is eventually dying down with some few ripples in the end. But this confirms that this is a low pass filter. So the Arduino code first has an initialization of the data that we work with. And this particular line signifies the baud rate, which sets up the communication between your Arduino and your computer. Now you have to traverse 1,000 data points to get a moving average at each data point, right? But an issue arises if your data point is at a data point of, say, between 1 to 8, because ours is an 8-point moving average. So if it is at a value of 3, we have to worry about values at a data point of -1, -2, -3, or -4, which doesn't make any sense because you don't have the data points, and B, there's nothing, you can't go back in time to the point where you haven't measured anything, right? So in that case, what you do is you assume that the response of the system at the time before you start measuring is 0. So you start padding zeros at the start, and hence what this does is it eventually just pads zeros at the start. So if I is less than 8, then what it does is it just sums all the values till that and then divides it by 8. Similarly, if I is greater than 8, then all we have to worry about is just j values before it and then divided by 8 for the output. So the plots that are derived from this Arduino code can be seen here. Now, what is a derivative filter first order difference? So a derivative filter first order difference is a high pass filter whose mathematical expression can be observed here. In the Z domain, the equation is this and the transfer function is this. So it has 1 0, and that 0 is present at z is equal to 1, and one pole which is present as z is equal to 0. Now the magnitude and phase responses can again be obtained using the same procedure as we described before by substituting z is equal to e power j omega and then getting the magnitude and phase responses respectively. Now the question arises that why is this filter a high pass filter? So let's just take this particular point, right? This point. Let's take suppose x equal to 1, and let's say that we want a derivative filter at x is equal to 1. So what we do is y is equal to x1 minus x0, right? So what you do, 1 minus x1 minus x0 gives you what? A 0. So you just get a 0 value in this range, right? So but if you look at this entire signal, wherever you take a difference, you're going to get a 0. Now let's look at this signal. If I take these two values, I get some slope, some or rather some particular value that you have, and since it's a first order difference, you know that there is a particular slope, right? Now let's look at this signal. So between this, let's just take this point for now. So the difference between this point and this point is not much, right, in terms of the x domain, but in the y-axis, the magnitude changes rapidly. So slope of this line is very high. So what does that mean? If I take the value of this and subtract this particular value, I get a very high value. So we can observe that as the signal is increasing in frequency, since the slopes are rapidly changing as the frequency increases, the derivatives also will rapidly change, and hence you'll get a higher magnitude. So we can say that a derivative filter is a high pass filter, and this can be further confirmed by looking at the magnitude response of this plot. So these lines remain the same as before, and again the issue remains that what happens if you get only the first data point, because there is nothing you can't subtract a data point of -1, right? So all you do is you make that you either ignore that data point or you can pair it with 0. In my case, I've just ignored that data point, and if it is greater than that first data point, all I do is I subtract that particular value with its previous value, and this entire thing runs for 1,000 data points because we have 1,000 data points. Printing this prints the original signal, and this prints the response, which is ARRI minus ARRI minus 1, which is xn minus xn minus 1, and this plots it as one single plot. So this plot can be seen from this particular figure. Now what is a derivative filter 3-point central difference? So a derivative filter 3-point central difference is a band pass filter, which is surprising since it's still a derivative filter. However, and you would expect it to follow the same behavior as a derivative filter first order difference, right? You would expect it to follow behavior that is similar to this. However, this is a band pass filter, and we will understand an intuition of why it is a band pass filter as we move on. In this z domain, the equation is this, and the transfer function is z square minus 1 upon z square. So there are two zeros and two poles. The zeros lie at z equal to 1 and z equal to -1, and the two poles lie at 0. The magnitude and phase responses can be obtained from the same procedure as before, and this is the diagram of the poles and zeros. Now, intuition of why the filter is a band pass filter. So the intuition is a bit shaky for this one, but it can be obtained through a bit of careful thinking. So for this particular signal, irrespective of which difference you take, is going to be 0. So you don't worry about this for now. Now let's look at this particular signal. If you look at these two data points, if this was 0, this is 1, this is 2, and I want to compute the difference at the second data point, right? So suppose y2 is equal to x2 minus x0. What do I get? I get a 0. If I move a little bit this side and I do the same thing, what do I get? I'll probably get this I'll probably get the same thing, right? Because all I'm getting are zeros at this point. Because at x0 the value is 0, at x1 the value is 0, at x2 the value is 0. So I get a flat line again, which is the same as what we got here. But let's look at this particular figure. If I take one point here, the second point here, let's take this is my second point and this is my first point. So now this particular thing the difference just gives me the slope, right? And the slope has a definite value which has a particular magnitude. So as you can see, from a frequency of 0, the response is increasing, and to a higher frequency the response is decreasing. Now this can be thought of as, imagine though this is a unit of time. So if my time period of the signal is much less than this, which is happening in this case, what will happen is every single time I'll probably get the same repeated value, and the subtraction will give me a very small value. But if my time period is such that it is slightly higher than a time period of 2, then we will get a definite value. Hence, it is a band pass filter. Now, this can also be confirmed by looking at the magnitude response, which is this. Now, the Arduino code is the same as the previous one, except that there is a padding of 0 that has been added here, and instead of a value of 1, there is a value of 2 as compared to the previous code. Now, these are plots that are derived from the Arduino code. Now, a question that may arise is, what is the practical use of this filter, right? Or what is the practical use of any of these filters, and how can you actually use them in real life? So a signal, now the data that we have obtained is from a PPG sensor. Now any signal that you have consists of a lot of noise. And that noise is not limited. There can be like baseline noise, baseline drift noise, rather, no, and high frequency noise or low frequency noise, etc. So the data we have, we can say that our data firmly consists of a noise-free signal along with a baseline drift and a high frequency noise component. Now, what is a baseline drift? So baseline drift is if you're measuring the data for a particular instrument and suddenly the mean of that signal is increasing and then decreasing, or the mean of the signal is changing, the statistical parameters are changing, then that means that there is a drift. So that can be because of motion, or the instrument is erroneous in the first place. So class example is this. Imagine you have a PPG sensor and you are measuring your heartbeat. But if your hand keeps moving, you might be adding an increased amplitude, which itself gives an increased amplitude to the statistical parameter of the signal. Hence, the mean of a signal is varying, which is something we don't want. Hence, we have to remove this baseline drift, and that can be obtained by taking an average of the signal over a longer period of time. And these noise high frequency components can be easily filtered out by taking a low pass filter. Now, getting the baseline drift is pretty easy, because all you have to do is you need an L point moving average where the L is very, very high. But getting the noise, the high frequency noise, is kind of difficult. And difficult in the sense that you might want to, depending on how the fidelity level that you want, you might want to increase the filtration or decrease the filtration. So an extreme method of filtering this is, first you take the data and subtract the baseline drift. So you have your statistical parameters are perfect, your mean is perfect, and it's fine. Now we pass this data minus baseline drift to a moving average filter. So what does that give you? That gives you a signal that has gone through a low pass filter, and all you have are low frequency components along with medium frequency components. But let's assume you want to remove these medium frequency components also. So what you do is, this data that you have got, you pass this through a derivative filter. So now when you pass it through a derivative filter, which is essentially a high pass filter or a band pass filter, you have all these medium components, right? Medium to high components. And now you take this medium to high components, subtract it from the data minus baseline drift that you had passed through a moving average signal to get a noise-free signal, which has a very high fidelity. So the Arduino code for baseline drift is the same as moving average code, but just that the data points are very high, and this is the baseline drift. So you would expect the mean to be around 0, right? Because a PPG signal measures the heartbeat. So if a person is not doing any activity, the mean of that signal should more or less remain constant. However, there is a baseline drift because probably of the motion of the person or the actual biological breathing and breathing out that causes this drift. And getting the medium to high frequency components can be obtained by first taking a difference and then getting the moving average of that. So in the description that I've written here, the sequence is different, that you first take the moving average and then pass it through a difference filter. However, since you're designing a system, irrespective of the location of the filter, the output remains the same. So the signal you get after doing this, after sending it through a difference filter and then sending it through a moving average filter, is this. So that is the end of the lab video. Thank you for your time.